We are now ready to study chemical kinetics. So we've talked about reactions, we've talked about stoichiometry, and we just finished up thermo, and those had to do with, what are we making, how much of it are we making, and thermo really comes down to will the reaction occur or not. Yes, we had bond energies, yes, we had a lot of other things there, but it's really the fundamental is this reaction favorable or unfavorable, but it doesn't tell us anything about when we can expect it to happen. We used diamond turning into graphite as an example. That is thermodynamically favorable, but it's not going to happen quickly. What we're talking about now isn't that stuff we talked about, it is the how fast. So as we get into kinetics, the delta H doesn't matter. The delta S doesn't matter. The delta G doesn't matter. Equilibrium, a lot of those other things that we're starting to get into don't matter. It's just, is it fast or is it slow? So this could be a reaction that is unfavorable that we're forcing to happen. And as we're forcing it to happen, is it happening quickly? Is it happening slowly? Or a reaction that occurs on its own, quickly or slowly again. So kinetics, another way to say that is just reaction rate. We did a little bit of this in first year chemistry, basically going through the stuff we're going to go through in this first video, and then you'll see there's a lot of new stuff we'll be able to add on top of that. But reaction rate, just how fast the reaction occurs, how quickly your reactants go away, how quickly we turn those into products. And there's a couple factors that change that. So we've got... let's scroll down, see if we can get all 5 on the screen here. The factors affecting reaction rates. The first one is, what are the reactants? The nature of those reactants. Basically meaning, what are we doing? What is the reaction that we have? The first thing about those is the state of matter. If they are aqueous, they're very freely moving, and they're already ions. They've already gained or lost some electrons. So those are going to be the most reactive because they're in the state most ready to mix. Gases can also react very quickly because the molecules are moving rapidly. Liquids are freely moving and freely mixing, but the molecules have much less energy and are moving much more slowly. And then solids, there's little motion. So a lot of times, if you're reacting solids, you're going to expect the reaction to start much more slowly because the particles are moving more slowly. Very simple, very straightforward, easy multiple choice, hopefully a very easy explanation. The chemical identity has a little bit more to it. It gets into a little bit more of the chemistry. It brings in some thermo, it brings in some periodic trends, so we're going to see some other stuff here. The strength and number of bonds to be broken or made. If we're breaking very strong bonds, it's less likely that that's going to be able to happen because so much energy needs to go in. So at any given time, fewer of those bonds are being broken. If we need to break a lot of bonds, it's going to take more time than breaking just a few of them. That's pretty straightforward and more or less common sense. The identity of the element. The element, basically where it appears on the periodic table, tells us a little bit about its electronegativity and its ionization energy. And you may forget this, but when we were looking at chemical reactions in Chem 1 and the periodic table and periodic trends and all of those things, we looked at electronegativity. That's how good a element is at attracting electrons in a chemical bond. Nonmetals generally react by gaining and attracting electrons. So fluorine is one of the most reactive. In fact, it is the most reactive nonmetal. Francium is the metal that loses its electrons most easily. In fact, francium, it's very rare, very radioactive, so it's not something you'd ever really see react. But it's good to think about these because here we're kind of in the top right of the periodic table. Here we're in the bottom left. So the closer to those corners you are, ignoring the noble gases, knowing that those are not reactive, you can get an idea of how reactive the elements are going to be there. And I mentioned electronegativity, but ionization energy is what determines that francium is so reactive. Francium loses electrons very, very, very easily. not very much attraction for them, lots of energy levels, very far from the nucleus. So that's what makes that one that reactive. The molecular complexity, the smaller it is, the easier it is to combine, react, and run into something else. Um, Whoops, there we go. And let's see, strong versus weak in terms of acids and bases. That's a really good thing to think about. And it goes back to some of these other things here. When it's strong, we already have everything aqueous. We have lots of ions. When it's weak, a lot of it's still in its molecular form. It hasn't been broken apart yet. So if you have a strong acid, it's got the hydrogen ions already free and ready to react. Whereas a weak acid, it can keep reacting. We can still see the same basic reaction. It can give away hydrogens. It's acidic, but those hydrogen ions are still bound, are still bonded to the rest of the molecule. So we have to break that bond. These other four things are definitely things we looked at in first year chem: the concentration, surface area, temperature, and catalyst. And I just want to kind of refresh ourselves on these. We'll spend a lot more time on a few of them. The concentrations, these are great things to have in your mind and kind of be ready to explain because it's great free response questions. So on quizzes, on tests, it's something you'd have to explain. If you have a higher concentration, that means you have more molecules in that given area, and those molecules can collide more often, and when they're colliding, that's what's causing our reaction. Concentration, specifically molarity, is something we would look at for aqueous things and for gases, but we can't calculate a molarity for a liquid or for a solid. If we have water and I pour more water in it, it doesn't get more watery. It still has the same number of H2O molecules per volume. So I'm not changing the concentration because there's not more water molecules in a given amount of space. There's just more total molecules. Same idea with the solid. We don't have more particles per given space if I get my sample larger, so I'm not changing the concentration. So definitely, as we're looking at concentrations, we're thinking molarity, we're thinking aqueous. Most of the time, sometimes we're looking at and thinking about gases. So how many molecules are in a given area? With solids, and to a much lesser degree liquids, so mostly solids here, we look at the surface area. Not how many particles are there, but how many of those particles are exposed. That's a very key word. That's an important part of this, that exposed molecules. Because if you just say there's more molecules to react, that's not necessarily true. Make sure you are getting to the point, make sure you're saying what you're supposed to be saying, but you're not saying something incorrect. We don't necessarily have more molecules, but those same number of molecules are exposed to one another now. So we can have more collisions in a faster reaction. This part is same. We'll use the words heterogeneous and homogeneous a few times throughout this unit and then a couple times in equilibrium, but it just has to do with exactly what it had to do with mixtures, which was, is everything in the same state or different states? Can you notice different things? So if we had a solid, we were dropping it into a liquid, so like a metal dropped into acid, that will react. But it only reacts at the surface of the solid, and the more surface we have, the more exposed molecules we have. So like powdered zinc reacts very quickly, whereas a big block of zinc, only those outside edges. So just a quick kind of cheesy little drawing here. If I've got this square here of zinc, only this surface, this surface, this surface, and the other three you can't see can react. But if I've got all this, if this is in tiny little dots here, each of those dots, every side of that dot can react. So we'll see a lot more reaction there. So it's all about what's exposed, and that's where we think about solids. Probably the most important of all of these is understanding and applying temperature. This connects us to thermo, but it's not necessarily always used in the same way as thermo, but it's a good a good connection, a good way that they bring those two topics under one question. So let's see here. We know, hopefully we know, that hotter particles are moving faster. Temperature is a measure of average kinetic energy. So if the particles are moving faster, they collide more frequently. And if they have more kinetic energy, that collision is more powerful. So we have more collisions. And those collisions are more powerful. So we'll see this graph a few times, but this is very, very important here. So a couple things was that and more forceful collisions. And this graph right here, this is called a Maxwell-Boltzmann distribution. You don't need to know that by name, and I'm not sure if I could spell it, so I'm not going to write it here. But these are two different things, two different samples with the same number of molecules. So if we were, there's a little bit that kind of gives some nods in kinetic to more advanced math, to some calculus, and this is an instance where that happens. We're looking here at the area under the curve for each of these. So the area under the curve is the same. If I remember right, that would be the integral. And if that's incorrect, I apologize to you and your math teachers. But we've got the same number of molecules, or the same area under the curve in both instances. But as we look at what our axes are showing us here, we're seeing how many molecules, the fraction of molecules that have a certain kinetic energy. Under the blue one, a lot of our molecules, most of our molecules have this much kinetic energy. On the red one, the majority of our molecules have this much kinetic energy. And as you look at this graph, there's kind of a common mistake or a common misconception. People see this graph and they think, okay, the taller one, that's the hotter one. But here, as we're moving further to the right, more kinetic energy is hotter particles. What happens is as they heat up, as we're at that higher temperature, we actually have a wider distribution of the kinetic energies. We have a larger number of faster moving particles. So instead of all of them clumping up here at this speed, there's more at this speed, but then there's way more even at these hotter speeds. And what's important about this graph, and we'll get into this with activation energy, with some other ideas, is these collisions have to occur. That line wasn't straight. And there, we're kind of straight. With a certain amount of energy. On the blue line, there are some molecules that have that much energy, but the red line, there are more. A larger number of molecules are under that section of the curve, so we've got lots of collisions in both cases, but the red line represents the collisions that are being productive, the collisions that are giving us the products that we want. And the last factor affecting reaction rate is a catalyst. And you've heard about catalysts, and this is one of the things that a lot of people come in with kind of a basic understanding, but also a basic or some misconceptions about it. So let's just, for now, hit kind of the highlights, and we'll definitely come back to this. It speeds up a reaction, but it's not considered a reactant, it's not considered a product. There are some terms here. They're used in what's called an intermediate step. It's used throughout the process, so it does go away, but it comes back because it's regenerated later. And when we say reaction pathway here, we're talking about not just, okay, well, what are we starting with, what are we ending with, but how do we get there? So what the catalyst does is it gets us there in a new way and in a way that requires less energy. The most common mistake with this is what we see right here. It lowers the activation energy, but people say, well, the catalyst speeds everything up. That's true, but it's not speeding up the particles. What it's doing is shifting this line. Right here, let me look at this. Right here, this is how much energy was needed normally, but if I put a catalyst in there, that line shifts to the left. So now, if I look at either my red or my blue, my red here, more of the molecules are reacting. It's not that they're moving faster, it's not that they're colliding harder, it's not that they have more energy, it's that I created a new condition in which not as much energy was required to get there. So, a new, different scenario. You'll see a little bit of this or more reference to this now than there used to be. Kind of some connection to biology here, enzymes or biological catalysts. So for those of you who know a lot about enzymes, AP Bio, etc., you'll be comfortable with that. But it doesn't really affect much of what we do other than you're going to see that word. So we're going to talk about the collision theory, which is kind of the step-by-step idea of what's happening when this reaction occurs. So we talked about the factors that affect it and kind of made some assumptions or built upon what you already knew. We've got particles, they have collisions, that affects the reaction. But taking even a step back, so maybe these two could have been in a different order here, is why are we looking at the collisions? So there is a three-step or three things that must be true in order for something to react. And not just concentration, surface area, temperature, whatever. That's how we change it. But when we're reacting, three things must occur. The first is that the particles have to run into each other. If you have a bunch of oxygen in one beaker, a bunch of hydrogen in the other beaker, and the beakers are closed, you're not going to make water out of them. The hydrogen and the oxygen have to come into contact with each other. Here it says only two particles collide at a time. That's what you should have in your mind. There is very, 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 very rare instances where we could have three things colliding at the same time, but we'll talk about what that is and why that's so rare. But there's also the chance that two things aren't colliding. In a decomposition, it could just be one thing breaking apart. And as we get into the more advanced stuff here, we'll see that that's even pretty rare. A lot of times we've got some in-between things happening, but we could just have one molecule that's rearranging itself. But whatever it is, your reactants have to come into contact with one another. If they're not in contact, they won't react. That's simple, that's obvious, but that's sometimes one of those easy points that people overlook. The second thing here, and depending if you printed this in color or not, or if you even printed it, you may not see this here. They have to collide with the right orientation. So we've got NO3 and CO, and NO3 and CO. In both cases, they're colliding, so that hits step one. But in this one, the O is coming into contact. In this one, the C is coming into contact. This one says reactants aren't facing the right way, molecules bounce off, no reaction. It doesn't matter how hard they hit each other. This oxygen doesn't want to bond with anything there, so it won't break bonds, it won't make bonds, it will not turn into reactants. What is supposed to, or what wants to happen, is this C wants to come in and take one of the O's away and make CO2 and NO2. So we have to have them oriented correctly. And I forget if it was a practice test where I saw it, but there was something where this was an explanation. It may have even been an AP exam a few years ago where it was talking about, well, what has to happen? So this is a simple thing. The molecules have to collide. They have to collide correctly. The atoms have to have, you can use the right word orientation, or you could use just a description of the right atoms have to hit the right things. And if you're having a hard time explaining this, you can do a drawing. It doesn't even have to be as complex as this, but if you want to say, well, this C needs to hit an O, then draw this exact thing, that only when the C hits the NO2, not when the O hits it, will you have a reaction. Drawings help a lot, and they don't have to be the most complex chemical drawing in the world. It can be, and sometimes should be, just a very simple sketch, kind of connecting your thoughts. And the last thing here that must happen is they have to collide correctly, they have to collide with enough energy. We've already talked about the term activation energy when we were looking at temperature, but the definition here is how hard they have to collide. The reason they have to collide with a certain amount of speed is that we've got protons and electrons here, we've got protons and electrons here. They're repelling each other. We have to get them close enough together that we can break bonds, that we can make bonds. And this is a similar reaction here. This one's NO2 and CO. But as these are coming together and as they're lining up and as they're getting close enough, we're breaking bonds, we're making bonds, but that can only happen if these molecules have, in this case, 134 kilojoules of energy per mole. That's the activation energy. So we've got our reactants to turn into products. We break some bonds, we make some new ones. We know that from thermo. Energy in, energy out. This is exothermic overall. But what we're doing here is, here they're coming together. And this sometimes is a little bit misleading. I don't necessarily like the way that this one's drawn where it shows a bond being made, but we're putting energy in because we know that breaking bonds requires energy and making bonds releases it. But what we can think of here is we've got our starting components, and this is kind of our chemical dressing room. It's not necessarily these 5 atoms all bonded together, but it's the broken up pieces of these as they turn to that. So we've got something at the beginning, we go into the dressing room and we're making some changes here, and then we come out with something new. This is our activated complex, or our transition state, reactants, products, and if we don't have enough energy, we won't get over that hill. If it's too cold, we won't get over that hill. A catalyst can affect how tall that hill is. We'll get back to that. But we have to have that energy. So heating it up doesn't make this hill smaller. Heating up doesn't make this hill bigger. Heating it up means that more of our molecules make it over the hill. They have enough kinetic energy to run into each other to do what they're supposed to do. A catalyst changes the height, but changing the temperature just means that the height as it is, it's easier to get over. And if we're thinking about this in terms of the dressing room metaphor here, the kind of two differences there, a catalyst would be, okay, these clothes went on sale. We now have a lower path, so more people are going to buy those things because it costs less. The other option, and, excessively cheesy here, the other option would be just, it's not that we changed the price, it's that now everybody here has more money, so more people can buy those things. So we aren't making it easier to get over the hill, we're just making it so that more things can do that thing that still is hard, not changing the price of doing that. So that's the very basics of this. What is reaction rate? What are some things we can do to speed it up or slow it down? And I didn't even mention that, but I said these things speed it up, so the opposites would slow it down. Hopefully that was obvious. And then kind of connecting at the molecular level. From here, we're getting into somewhat uncharted territory. This is no longer the Chem 1 stuff. That first page in a little bit, was Chem 1. Now we've got about 10 more pages of new kinetics. It's not hard, but it's new stuff. So make sure you're really paying attention to the videos, trying the practice problems, asking questions, all of those things. Because it can be one of the easiest topics on the AP exam.